Oscillations are a common and important phenomenon in mechanics and elsewhere. But what mathematics can be used to model oscillations? This can. You'll see in a later unit why these equations may be appropriate models in mechanics, but in this program we're concerned with the solution of these equations. In particular, we'll be looking at the graphs of the solutions, because graphs are helpful in enabling us to visualize the information we get from such equations. So, let's get down to the maths. Alpha, beta, and gamma are constants in this equation. We'll start with homogeneous equations, move on to inhomogeneous equations. Actually, nothing more complicated than this. But let's start with something reasonably straightforward. How can we solve this?
The method I'm going to use works for any homogeneous equation, so we may as well look at the general case. I'm looking for a solution to this equation. And that means that I'm looking for some function, y of x, which when I substitute it in here, will give me naught. So somehow these three terms have got to cancel. Well, one way of arranging that is to set y of x equal to an exponential function. Because then, when I differentiate, I'm going to get the same exponential function back, but multiplied by the constant lambda. And if I differentiate again, I'll still get the same exponential function back, but this time multiplied by lambda squared. Well, that means that when I substitute these terms back into the differential equation, I can pull out a common factor of e to the lambda x. And I'm left with this. And now I can cancel off that e to the lambda x, because the exponential function is never zero, so it'll just cancel. Then I'm left with this equation, which is called the auxiliary equation. It's a quadratic equation, so it's got two roots. And I'll call them lambda 1 and lambda 2. And that means that I've now got two solutions to my differential equation. I've got y of x is e to the lambda 1x, that's putting lambda 1 into my trial solution. Or I can put lambda 2 in, and both those functions satisfy the differential equation. But they're not the only functions that satisfy that equation. In fact, any linear combination of them is also a solution. And in fact, any solution of the differential equation can be written in this form. It doesn't matter what values a and b take, they can take any values, and I'll still have a solution. So a and b are called arbitrary constants, and this is the general solution of the differential equation.
Let's see if John's method works for this differential equation. We write down the auxiliary equation, and then we solve that, and then the general solution of the differential equation is a combination of exponential functions. The graph of this will be a combination of an increasing exponential, something like this, and a decreasing exponential, like this. The graph of a combination of these could take a number of forms. Here's one possibility. Well, that's fine, so far as it goes. But I've been making an assumption that that constant k is positive. If it's negative, we're going to have to be careful about those square roots. If k is negative, we get imaginary solutions of the auxiliary equation. Then we can write the general solution of the differential equation in this form. Or alternatively, we can write it in this form, because those complex exponentials are each a combination of a sine and a cos. And everything is real here, as we'd expect. So if k is negative, the general solution of the differential equation takes this form, a combination of sinusoidal functions. I want to look a bit further at this, so to simplify the algebra, I'll replace k by minus omega squared. When we do that, we're solving this differential equation. The general solution will now take this form. That's a combination of sinusoids, so it can also be written as a single sinusoid, like this. With the general solution written in this form, the arbitrary constants are a and phi. Note that the value of omega is fixed by the differential equation itself, but the values of a and phi are not. Whatever value they have, that's still a solution. What does the graph of this solution look like? It's a sinusoidal oscillation. Remember, we're talking about the solution of this differential equation. Let's look first at the parameter omega. That's called the frequency of the oscillation. If omega is larger, we get this, high frequency. If omega is smaller, we get this, low frequency. This is the period of the oscillation. That's the time it takes the oscillation to repeat itself. Now, that parameter omega is determined by the differential equation itself. So let's fix omega and look at the general solution of the differential equation and the way the graph depends on the two arbitrary constants, a and phi. Let's vary phi. Phi is called the phase of the oscillation. The dotted cosine curve has zero phase. The solid curve is shifted in the x direction. The amount of shift is phi divided by omega, so it depends on the phase. What about A? Let's vary A. Large A, small a. A is the amplitude of the oscillation. So, the general solution of this differential equation is a sinusoidal oscillation of angular frequency omega. The general solution contains two arbitrary constants, the amplitude, a, and the phase, phi. Now, nothing we've said so far will determine values for a and phi. We'll only be able to do that if we have additional information about the solution. For example, suppose we require that y is 1 when x is 0. Will this determine values for a and phi? Here's one solution satisfying that condition. And here's another with different values of a and phi. So there are other solutions with y equal to 1 when x is 0. So one condition does not pick out a single solution of the differential equation. It doesn't fix values for a and phi. But suppose I specify the gradient of the solution at x equals 0, as well as its value. Now I've specified values for the function and its gradient at x equals 0. That other graph doesn't give the right value for the gradient at x equal to 0. The two conditions together do give a unique solution.
Well, let's see how that works algebraically. This is the general solution to the differential equation. It includes two arbitrary constants, a the amplitude and phi the phase. And what I want to do is to pick a and phi to satisfy these conditions. Well, actually, I find it more convenient to use the other form of the solution that involves sines and cosines. where C and D are the arbitrary constants here. Now let's just use one of these conditions, the fact that y is 1 when x is 0. So I just put in y is 1, and I have to put in x equals 0 here. The sine of 0 is 0, and the cos of 0 is 1. So I'm left with d has to be equal to 1. And that's found one of the arbitrary constants here. But to find the other one, I need to use the other condition. So what I'll have to do is actually differentiate this general solution to see what I get. Let me do that. Get that. And that. And then again, I just substitute in dy by dx is 0, and then I have to put in x equals 0 here. So I get c omega times 1 minus d omega times 0. Now, the omega here is just some parameter. It's determined by the differential equation itself. So that's not equal to 0. And that means the only way I can satisfy this equation is for c to be equal to 0. So I found the other arbitrary constant, c is 0. And I can put that into the general solution here to find out what y is. Y must just be 0 times sine x plus 1 times cos x. So it's just cos omega x. Now that's the solution that satisfies the original differential equation and these two conditions. Now there's something rather special about these two conditions. They're called initial conditions. And the reason for that is because the value of y and the value of dy by dx are both specified at the same initial value of x. Now, whenever I have initial conditions like these, I can go through a procedure like this and end up with a unique solution to the differential equation. But what if I have something more complicated? Supposing I have the value of y specified at two different points. Do I still have a unique solution? Suppose we require the solution to be 0 at these two values of x. We can make the solution do that, but in so many different ways.
So, if we impose two conditions at the same value of x on the solution of this differential equation, we always get a unique solution. Things may not work so well if the conditions are at different values of x. However, let's get back to the graphs of solutions. For this simple differential equation, the solutions are pure sinusoids. Now let's look at something a bit more complicated. The 2 is just there to simplify the algebra later on. So far, we know about the case where alpha is equal to 0. What happens if alpha takes a positive value? Let's start with alpha equal to 0 and increase alpha. Let's see that again. The first change is that we get an oscillation whose amplitude decreases as x increases. As alpha becomes larger, the decay is more sharp. The frequency becomes smaller, and eventually the oscillations disappear entirely. Why does that happen?
Well, if we look at the auxiliary equation, we can see why. The auxiliary equation for this differential equation takes this form. And as usual, it's a quadratic equation, so it's got two roots. And I can find those roots by using the formula. I get that. Now, if alpha is greater than omega, then this is a positive quantity. I'm taking the square root of it, so there's no problem in doing that. The square root of a positive quantity is a real number. So this is real when alpha is greater than omega. But suppose alpha were less than omega. In that case, I'd be taking the square root of a negative number. And then it's really more convenient to write the roots like this. That makes it quite clear that I've got complex roots when alpha is less than omega. Well, what does all that mean for the solutions of this equation? If I take a typical solution, e to the lambda x, and suppose I take the case where alpha is greater than omega, then in that case, the roots are real. Lambda is real, so this function is really just an exponential function. But supposing I take the other case where alpha is less than omega, in that case, the roots are complex, and I can split up the solution like this. It's the product of these two terms. Here again I have an exponential function, but it's multiplied by this. And these terms are sinusoids. So the solution involves the product of a sinusoid times a decreasing exponential function. With alpha equals 0, a pure sinusoid. Alpha between 0 and omega, sinusoid times decreasing exponential. When alpha reaches omega, the oscillation disappears.
So far, we've said nothing about initial conditions applied to this equation. In fact, for all values of alpha, we've been looking at the solution satisfying these initial conditions. That is, that at x equals 0, the value of y is 1 and the gradient is 0. Now, let's fix the value of alpha for now and look at some different initial conditions. Here's the oscillatory case. We can satisfy different initial conditions like this. The shape of the curve's always the same. It's just a matter of how we start. In this case, the solutions are decreasing exponentials. A combination of exponentials can be made to satisfy various initial conditions. The shape of the graph varies a bit, but for large x, we always get that characteristic exponential decay. But let's move on to an inhomogeneous equation. Now I've got a term on the right-hand side of the equation, a sine term. I'm going to stick with this particular equation with these particular coefficients and that particular right-hand side. And let's look at a solution of this equation. It looks a bit complicated. But notice that after a while, it settles down to a pure sinusoid. Now, let's see what would be left if we subtract that sinusoid from the total solution. So here's the remainder. And it looks familiar. It's a decreasing oscillation. So the solution of that original equation is the sum of two parts. That sinusoid and that other bit, which looks like the graphs we had before.
Well, that's what the graphs seem to say. But is it true? Well, to see that, I'll write down y as the sum of two terms. And then I'll substitute this into the differential equation. Well, if I do that, I get this. You see, substituting y in here gives me these two terms. And these two terms come from substituting into dy by dx. And these two terms come from the second derivative. So, all I've really done is to rearrange these terms involving z, collect those all together, and to collect together these terms that involve f. Right. Well, suppose I let this bracket be equal to naught. If that bracket is equal to naught, then this bracket must be equal to sine 2x. And that's just the original equation I started off with. Now you can show for yourselves, I'm not going to do it here, but you can show using phasors that there is a sinusoidal solution to this equation. So that f is a sinusoid. But what about z? Well, z satisfies this equation. And we know about the solutions to equations like these. This is a homogeneous equation, so its solution is either a pure exponential or it's a sinusoid times an exponential. And which it is depends on the values of these two terms. Actually, in this case, alpha is equal to 2 and omega is equal to the root of 5. So alpha is less than omega, and the solution I want is a sinusoid times an exponential. And that's actually the general solution to the equation. It's always of the form a sinusoid plus a sinusoid times an exponential.
Here is f, the pure sinusoid. And here's z, the sinusoid times a decreasing exponential. We call f the steady-state solution of this equation. That's because when x is large, f is the only part of the solution which is left. Z is called a transient because it dies away as x increases. So, for an inhomogeneous equation like this, the solution is the sum of two bits. There's a purely sinusoidal bit, which we call the steady-state solution, and that is determined entirely by the differential equation itself. And to that, you add a transient that satisfies the associated homogeneous equation, and the initial conditions will affect only the transient. And don't forget those graphs.